1C. And I left the little piece off because I thought, you know what, let's just talk about this on Monday so people aren't getting all weirded out by this. For C over here, we did all of our wonderful factoring so that we could figure out, and remember, here's how it works. You start on the bottom and you say, what can't I do here? Because those would be vertical asymptotes or holes. And we said, well, -2 is out, so that's going to be a vertical asymptote. And that's because it doesn't cancel. -1 is out, and that's because it's going to be a hole. And they talked about removable and non-removable, but really what we care about is this is going to be a vertical asymptote, and this is going to be a hole. So vertical asymptote x equals -2 and a hole. And then we went ahead and said, all right, the x-intercept is going to be -1, 0. Because if we put a -1 up here, we would get a 0 for the y. But this is the part I wanted to keep for today. We can't use -1 in this. Because, remember, the vertical asymptote in the holes give us our domain. So our domain would say x can't be -2 and x can't be -1. So if we want to put a -1, 0 into this, we can't because it's already been left out. So we would have to write none for that x-intercept. So go ahead and put a line through it and put none, and then write down, did we have the domain and range on yours? Because it looked like I had to erase or something. I kind of ran out of space. Maybe give yourself a big arrow to that. Now the y-intercept was fine because we put a 0 in for x and 0 was perfectly fine. There's not a problem with 0 in there. But we wouldn't be able to get an x-intercept with this one because the one that we did get, we can't use. That was part of our hole up in there. So there it is. Now, we finished up by saying if a rational function has a non-removable discontinuity at x equals a, if it won't cancel, that makes it a vertical asymptote. And that puts us where? Let's see. I know it didn't seem like we got real far, but we actually have covered a lot of stuff. So that's right here. A vertical asymptote. Doesn't cancel. Vertical asymptote, we put a dashed line on the graph at that spot and say, hey, I can't use this one. It's not going to happen. So usually we will catch it when we're graphing. You know, it will go, wait a minute, I'm not supposed to put a number here. Well, how did that show up? And we'll realize we couldn't use that number. Now, the vertical asymptotes of rational functions, and we talked about this on Friday as well, come from the denominator. You know, any factors that aren't going to cancel, and we see those factors, and we say, wait a minute, if I put this number in the denominator, I'm going to have a 0. We can't divide by 0, so that's not going to work. So in fancy math language, that's what this says. The graph of the rational function f of x equals p of x over q of x has a vertical asymptote at each real 0 of q of x. Notice that's the one in the denominator here. If p of x and q of x have no common zeros, that means if it won't cancel out. So if it won't cancel, we have to worry about that. If p of x and q of x have that factor, and that means there's the same factor in the top and the bottom, well, then we can cancel them out, and that makes it a hole. So if it cancels, it's a hole. If it doesn't cancel, it's a vertical asymptote. So down here, what we're just going to do is we're just going to talk about vertical asymptotes for these, because those are really important. We have to get those on our graph. And it says, what are the vertical asymptotes for this graph? And I don't even really take a look at the top to start with. What I'm looking for is this bottom factor? Because that's going to help me find my vertical asymptotes. Then I look at the top and I say, is anything going to cancel here? Is anything going to cancel in this problem? No. So we're going to have two vertical asymptotes. And they'll both be x equals something. And that something is the number that would make them 0. So if it's x minus 2, what number do we have to leave out? 2, because 2 minus 2 would make it 0. How about x minus 3? What do we leave out? 3. Can't use it. Those are our vertical asymptotes. So these two, 2 and 3, would go on our graph as vertical lines to show that those are asymptotes for our graph. Because eventually that's what we're going to do with all this information. all of the settings went really wacky on this thing over the weekend. So let's see how everything shows up here. So now we're going to do this again, but we're going to talk about, well, a little bit more complex. A and B are already factored for us, but C we might have to do a little bit of work for. What are the vertical asymptotes for A? First of all, already factored, is anything going to cancel? Nothing's going to cancel? So find the zeros of the denominator. X equals 1. Anything else? -3? Anything else? Nope, those are our two factors down here, x minus 1 and x plus 3. So 1 and -3. Now, if it's not coming to you as fast as it is other people, remember you could always set it equal to 0, add 1 to both sides, set it equal to 0, subtract 3 from both sides. Perfectly fine. That's absolutely fine. Take a look at B. Already factored, right? Will anything cancel? So that's a whole. That's not a vertical asymptote. That would be a whole. So what we have left is our vertical asymptote. So what number is that? -3. Now C is the one that I said, I don't think that's factored. One of them is factorable, isn't it? Which one? The top is. Okay, how do we factor x squared minus 1? What do you get? That's too long. Are there two numbers that multiply to -1 and add to 0? What are they? 1 and -1. So, is what we have in our denominator, is that a vertical asymptote or is that a whole? It's a whole, it's going to cancel. Well, we don't have anything left in the denominator. That means we don't have any vertical asymptotes. We don't get any. Sometimes it doesn't happen. Sometimes we can use all the x's we want. So there it is. Now this isn't going to allow us to use all the x's we want because this one has a hole. We know that at -1 we will have a hole in this graph. But that's another piece of information that will help us graph without having to use our graphing calculator until the very last second. Everything we know about it on. So a rational function can have any number of vertical asymptotes, but no more than one horizontal asymptote. So as many factors as we can find in the denominator, we can have vertical asymptotes. But the most we're ever going to have for horizontal asymptotes is 1. That's going to be it. Now, here's the other bad news. Horizontal asymptotes don't always work. Sometimes horizontal asymptotes work for 2 parts of a graph, but in the middle, it actually gets crossed. That's just hyperbolas. That's the nature of hyperbolas. They're unpredictable. So that's the reason we want to find all the stuff that we have been finding before we try and graph it. That way we'll know, hey, wait a minute, I must have pressed something in wrong because this just doesn't match what I know from the math. Because in the end, we truly are going to use our graphing calculators for these. So now, we have one more big box of info about these graphs. It says, horizontal asymptotes of a rational function. So this is the one where we get 1 at most. To find the horizontal asymptote of the graph of a rational function, compare the degree of the numerator m to the degree of the denominator n. So here's what they're saying. We're going to have an x to the something up here and an x to the something down here. But remember, degree is the highest power, so it has to be that first leading term that we're talking about. So here's what it says. If the degree of the top is less than the bottom, then y equals 0 is going to work, the x-axis. So if this is bigger than this, then we can write y equals 0 down as a horizontal asymptote. If m is greater than n, we don't get one. So if this power up here for the degree is greater than the one down here, we don't get one. Then, if the degrees are equal, here's what we do. We look at the numbers in front of these two terms, and we use them as a fraction for our asymptote. Now, this is not how I memorize these in order. Generally, how I memorize them in order is kind of the way I think of the number line. If the top is less than the bottom, it's y equals 0. If the top equals the bottom, then I get to use the little fraction. And if the top is greater than the bottom, then I don't get one. And that's the way I have them memorized as I go through. So what I did was I came up with a little cheat sheet, and this is not something you're going to be able to use for the test, but we've talked about this before. When you have to look something up repeatedly, your brain says, well, I better start remembering this. And this really takes us through almost all the stuff that we've talked about with hyperbolic graphs. X-intercepts, the y-intercepts, finding asymptotes and holes. So this is something to just tuck in your book after we go over it, whenever you're doing the homework. When we're doing the notes today, have it sitting out so you can look at it. Because the more you have to look it up, the more your brain is going to say, I'll just remember this because I'm sick of looking it up. So, starts right at the top. What is the degree? It's the highest power of the variable in the polynomial. So that's just to remind you what degree was. Number 1 says the x-intercepts are the zeros of the numerator, which is the top of the fraction. So if I go back, well actually, right up here, these that we're looking at. And I want to find my x-intercepts. I go right here and say, well, it's going to be at 2. This one will be at 2. This one would be at plus or minus 1 because when we factored it, those would be the zeros of the numerator. Vertical asymptotes are the zeros from the denominator that don't cancel. We might want to add that on there. They don't cancel. So for number 2, vertical asymptotes at zeros of the denominator at the bottom that don't cancel. And then horizontal asymptotes, back to the degree. If the degree of the top is less than the degree of the bottom, it's y equals 0. If the degree of the top equals the degree of the bottom, then we do this little fraction business right here. And if the degree of the top is greater than the degree of the bottom, we don't get one. Now, I didn't put everything on this list that we talked about. And that's because removable versus non-removable, we just need to know, does it cancel out? Is it a whole because it cancels? Or is it vertical asymptote because it doesn't? So now what we're going to do is we're just going to look at horizontal asymptotes. So I think, okay, horizontal asymptotes are all about degree. So I have to know what the highest power is. Let's see. Well, this one has a power of 1 and this one has a power of 1. Okay. If the degree of the top is less than the degree of the bottom, it's y equals 0. That's not that one, they're the same. If the degree of the top equals the degree of the bottom, then you do the little fraction thing. Okay, so that's a 2, that's a 1. Y equals 2 is my horizontal asymptote. So I just go through this list in my head each time that I want to find those horizontal asymptotes. All right, so it's about degree. Over here, that is x to the first. Okay. If the degree of the top is less than the degree of the bottom, then it's y equals 0. 1 and a 2. Yeah, the degree of the top is less than the bottom. There it is. It's y equals 0. Down to C. All right, that's a 2, that's a 1. Okay. If the degree of the top is less than the degree of the bottom, then it's y equals 0. If the degree of the top equals the degree of the bottom, then I do the little fraction thing. No. If the degree of the top is greater than the degree of the bottom, then I don't get one. I don't get one. No. And if you just go through list 3 or 4 times, your brain is going to start to remember that. And you just know right away, wait a minute, that one's bigger than that one. I will get one, you know, and you can go through that. Alrighty, here are some more. So I'm going to have you help me out. If you have to use the yellow sheet, use the yellow sheet. So there's some mystical little ones right there. Is the degree of the top less than the degree of the bottom? No. Are they equal? Then what are we supposed to do? A little fraction thing. There's no number here. It's a 1. So negative 2 over 1, which is negative 2. Let's go to B. Oh, there's no power on the top. What's the power? If the degree of the top is less than the degree of the bottom, y equals 0. Take a look at C. Again, there's our little 1 right there. The degree of the top is greater than the degree of the bottom. What do we put? None. We don't get 1. And don't ever just leave it blank, because leaving it blank says, I didn't know what to tell you, Cedar Home. But putting none down, that tells me you knew exactly what you were doing. You're not going to get 1. So, our essential understanding is we can get a reasonable graph for a rational function by finding all the intercepts and the asymptotes. Our objective was identifying properties of rational functions. Boy, oh boy, have we ever done that. We've got a long list of stuff we can find about these. But the second part of the objective is, hey, let's graph it. You know, let's see. Does this do all the stuff we know we're supposed to do? Now, like it says, we're going to find all the intercepts, all the asymptotes. It's probably still not going to be enough. So we probably are going to have to put in a few points on the graph. But that's what graphing calculators are, you know? And like I said, that's how we, in the end, are going to graph these. So grab your graphing calculator if you haven't already and have that stuff, all the algebra stuff down first. And if I punch it into my calculator and it's crossing stuff it's not supposed to cross, I know something's wrong. I punched it in wrong. So it says, what's the graph of y equals x squared plus x minus 12 over x squared minus 4? That's not factored. We need to factor that. All right. So, can you think of 2 numbers that multiply to negative 12 and add to 1? Or negative 3? How about x squared minus 4? We'll be back to that. X plus 2x minus 2. All right, so away we go. Let's start finding all the things we can possibly find here. And the first thing that I always start with is the bottom. I want those vertical asymptotes or holes right away. So, anything going to cancel here? No holes. Vertical asymptotes come from the denominator. So what are our zeros for the denominator? Actually, I usually stop right there and start graphing this stuff because I don't want to forget any of it. So x equals 2. Remember, it gets its name from which axis it karate chops. This is karate chopping the x-axis. All right, so far so good. That's actually a really big help. Okay, other things we want to know. Well, it doesn't have any holes. It has vertical asymptotes. So x-intercepts. Ooh, there's something about x-intercepts on the yellow sheet. How do we get those? Where the top is 0, where's that going to be 0? Come on. A little louder. 0's in the top. Negative 4 and 3. There it is. Let's put those on. You might want to grab a different color out of the bag if you don't have like a different colored pen. Try and have your asymptotes and your graph two different colors so it'll kind of pop out at you. Now those are actual points on a graph, those x-intercepts. The y-intercepts come from putting 0 into this thing. Now remember, that's where we can slash off the x's because anything that has an x in it is going to be 0. So back up here, 0, 0, 0, negative 12 over negative 4. What is that? 3. Okay, now use the same color that you just used to graph the intercepts for the x-axis, and let's graph our 0, 3. All right, last but not least, the last thing we talked about was horizontal asymptotes. Okay, let me go erase all of my stripes up there because I need to know the degrees. What's the degree of the top? 2. What's the degree of the bottom? 2. They're the same. What do we do? There's no numbers there for the little fraction thing, are there? They're ones. Y equals 1. Now this is an asymptote, so go back to your pencil here and let's put that on. So what I have up here in the red is stuff we're not supposed to cross. We're not supposed to get to that. But the stuff in the blue, that's actually supposed to be a part of the graph. So on the test, we're of course going to have a table there so you can put some other numbers on. But we're going to grab that graphing calculator and we're going to try to figure out where would this be the easiest to punch in with our graphing calculator. You know, should we punch it in just as it was? Should we punch it in all factored out? What do we want to do? It's actually easiest to punch it in from the original because what we have to do is use lots of parentheses if we start factoring. So just one set of parentheses for the top and one set of parentheses for the bottom. That's the easiest way to get it into the calculator. If we did it over here, we'd have to have, look at all these parentheses to get the calculator to know all that stuff goes together. That would not be a lot of fun. So let's punch it in and let's see if we were right about all this stuff. So parentheses, x squared plus x minus 12, parentheses divided by, parentheses x squared minus 4, parentheses. Little zoom 6 action. Looks like it fits, doesn't it? Let's make sure. Let's go to the table. And let's remember we said that negative 2 and 2 are asymptotes. So we better get an error message at those two spots. We'll look at that. Error and error. Here's another thing we know we did right. 3, 0. That was one of our intercepts. Let's check out the negative 4, 0. Did that right too. So everything we have up there matches. Now we just have to use the table and say, you know what would be really cool if I could figure out 1, 2, 3, negative 3 something. Then I would have enough to graph that branch there. So negative 3 is negative 1.2. Negative 3, negative 1.2. And notice I'm using the same color as I did for the intercept so that I know, hey, these are points that are on my graph. And we know what asymptotes are for. We're supposed to approach them, but never quite get there. So we just make it look like it's getting close to those asymptotes, but make sure you put arrows both ways. That thing goes forever. Now that middle part was kind of weird looking, wasn't it? Look at that weird part. It's like it's a little parabola that's not quite symmetric up there. Well, let's get a couple of points for that one. Let's see. A negative 1 would be good and a positive 1 would be good. So negative 1 is 4. And positive 1 is, well, 3 and a third, but 3.3 repeating. So we'll get those on there. 1, 2, 3, 4, and 1, 3, and a little bit more. And again, we know it's approaching the asymptotes. last but not least, we better get one more point over here with this little guy. This little guy was 3, so maybe 4. And that's 2/3, but 0.6 repeating. We're going to do decimals. And that would be right here, and that certainly fits with what we know about the asymptotes. Now we know we're right. Now, what if something doesn't show up the way it's supposed to show up? If you know your math is right, you punch something in wrong. But here's the one glitch. Remember what I said about the horizontal asymptotes? You might want to write this on your yellow sheet down here. Sometimes they don't work for the whole graph. So it's possible that sometimes we're going to graph this, and this middle portion will actually cross our horizontal asymptote. Not these two branches. They won't cross it. But we may cross it in the middle. It's just one of those things that happens with hyperbolas. There's just so much going on that occasionally they will cross that. In fact, we might see that in the next example here. I thought we had one that did that for us. Alrighty. Look at that bugger, huh? Let's start over again. Let's get all the good stuff.
Get some homework. We're good.
2 of these for homework, right?
Yeah.
All right. X squared minus 6x plus 5. So that's factorable? That's a maybe, isn't it? All righty. Can you think of 2 numbers that multiply to 5 and add to -6? -5 and -1? Okay, so let's start in the bottom again. Well, the first thing I'd check for is holes. Is that going to cancel? No holes. But that means we're going to have some vertical asymptotes. Where are they? 5 and 1. Okay, now this time let's find all of this before we go into that graph. Let's see. Next up, well, we might want to find those x-intercepts and y-intercepts. How do you find the x-intercepts again? I think it's on the yellow sheet. Where the top is 0, so where's the top going to be 0? -3. Y-intercepts. Remember how to do those? Make x equal to 0. Easier to do up here. All that's left is 3 and 5, so 3/5. All right, well now I think we're to the horizontal asymptotes, which are about degree. So what's the degree at the top of this thing? 1. If the degree at the top is less than the degree at the bottom, 0. So HAY equals 0. All right, so pick one color, and let's do all the asymptotes in that color. So that's 1 and 5 for the verticals. And then y equals 0 is the x-axis. So that's where we know our graph is not supposed to go. And then we want to switch colors and use the other color for stuff we know is supposed to go on a graph. Well, that's not as much as last time, is it? Well, but we'll know whether or not we're right or wrong when we punch it in. We've got to see this. So that's what we do. Again, we go back to the original, and we use a couple of sets of parentheses, and we hope everything we had is the right divided by parentheses x squared minus 6x plus 5. Zoom 6. Interesting. So we better check, huh? Well, look at that. Negative 3, 0. We were right. Even though it was an asymptote, that is a point on our graph. The other ones we wanted to know about were 1 and 5. So 1 looks good. That's got an error message. 5 has an error message. Good, good, good. And we said 0 was going to be 3/5. Let's see. 3/5 would be 6/10. Oh, look at that. Right on line. So now we just need, actually we probably wouldn't need any more for this portion of the graph, except what is going on over there? It's like the graph just disappears, right? So we want to make sure that our graph looks like it's just going to be right on the axis here. Or really super duper close to it. That middle portion we didn't have anything for, so we're going to have to go to the table. So we need something for 1, 2, and 3. And 1 is that error message. 2 is negative 1 2/3. 1.6 repeating. 3 is negative 1.5. And while I'm there, I might as well write down 4. Negative 2 1/3. And get that portion of the graph in there. So 2, negative 1.6. 3, negative 1.5, and 4, negative 2.3. And again, I'm doing these in the same color, but the other part of the graph, the branch, was graphed, so that I know, hey, that's an actual part. Then we've got to see some stuff on the other side of 5, because we've got nothing over there. So maybe 6 and 7. 6 is 1.8. And 7 is 0.83 repeating. But again, we know it's approaching those asymptotes, so we don't need a lot of points. 2 is good enough. We've got it. That's good stuff. And that's a lot to keep track of. But the good news is we should know, if we get enough information from the algebra, whether or not we punch something in wrong or not. You know, I try to go too fast on my graphing calculator sometimes, and I get something that doesn't match my math. I know I punched it in wrong. I go back and check it. So now, what is all this about? Well, we need to take a peek at the chemistry problem. Woohoo! That just made everybody real happy, right? So now that we found all of that good stuff, now what do? Oh, look at that thing. You work in a pharmacy that mixes different concentrations of saline solutions for its customers. The pharmacy has a supply of 2 concentrations, 0.5% and 2%. This function, right here, gives the concentration of the saline solution after adding X milliliters of the 0.5 solution, so that's this one right here, to 100 milliliters of the 2% solution. How many milliliters of the 5% solution must you add for the combined solution to have concentration of 0.9%? Oh my goodness. Here's what they're asking us. They're saying if you put 0.9% right here, what should we get? And 0.9% has to be changed into a decimal. So how many decimal places do we use whenever we want to change a decimal into something we can put in the, there we go, 2 places. 009, Bill's got it. Now, I don't want to punch in that mess they have up here, so what I would do is simplify it a little bit and say, well, 100 times 0.02, that just moves the decimal over 2 spots. That's a 2 plus 0.005x over 100 plus x. Now, we can solve this with algebra. know, hey, the y sub 1, y sub 2, and blinky thing, it still works. So we're going to make one of these y sub 1 and the other one y sub 2 and see where they hit each other. We've got to use parentheses for the top and the bottom, just like we were doing for the ones that didn't have all the nasty little decimals earlier. So let's see what blinky can do for us. 0.009. 2 plus 0.005x divided by alrighty. Now the fun part. The fun part is the window. Knowing what to set this to. Because negative 10 to 10 probably isn't a finer answer for us. So let's go to the window. Now, x is in milliliters, and you can't put a negative milliliters in something, so I'm going to put a 0 there. Milliliters, you guys, have you ever seen an eyedropper? You know, and one drop comes out at a time? That's about a milliliter. So it takes a lot of milliliters to make a change to something. So maybe we'll try 500 milliliters, see if that's enough. And then, obviously, we have to be able to see 0.009. So if we put 10 in there, that's way too big. I mean, if we put 1 in here, it might be way too big. But let's try it. Let's try 0 to 1 and see if that'll do it for us. So we want to see where they intersect. Let's hit graph. Nothing. 0 point, did I miss a 0? 2 plus 0.005x. Oh, here's why. I forgot. It doesn't show up because 1 was too big. Remember I said 1 was going to be really large? So let's try 0.01 maybe? Still too big. Do you see that little itty bitty thing in the corner there? Whew. 0.001. Yeah, we are. We're getting closer. So let's see. Let's try this. Y min of 0. 0, 0, 1. 0, 1. There it is. So let me switch back so you can see. So everything in this is really, really teeny except for the milliliters. So the milliliters are huge. I actually had my Y min and my Y max. That's why I said I'd rather do this stuff by hand than use a graphic calculator. But now we can get Blinky to find it for us. So second trace, number 5. Blinky's right in position, so enter 3 times. There it is, 275 milliliters. 275 milliliters. Well, good news, they have another one of these down below, so maybe I can get my Y's in the right spot this time. Here we go. Alrighty. Orange juice drink is not pure orange juice. It says what you're going to do is mix 10% orange juice with 100% pure orange juice to make a 40% orange juice drink. That little function gives the concentration Y of orange juice in the drink after you add X gallons of that juice. And we want to know how much do you have to add to get 40% juice. Now, 2 times 1 is 2, so it's kind of silly to leave that. And that's what we have so far. What we want to know is when is this 40%? How do you change 40% into the decimal? 0.4. numbers are not awful. But like I said, the book really wants us to get used to using the calculator for this. So y sub 1 and y sub 2. And we'll see what we get. Alrighty, so y equals 0.4. And then parentheses 2 plus 0.1x parentheses divided by parentheses 2 plus x parentheses. Now, a milliliter, remember, is what we had in the last problem, which is 1 drop of a liquid. Our gallons, 1 drop of a liquid. A gallon of milk is pretty huge, right? So let's just try like 5 gallons and see if that'll be enough. And our Y max, we want to be able to see 0.4. Maybe let's try 0.5. There it is. So from 0 to 5, because gallons are lots, but then 0 to 0.5 because we just wanted to see 40%. Second trace, number 5, bing, bang, boom. Blinky says you're going to have to add 4 gallons. Yikes. 4 gallons of 10% juice drink. I don't know why you want to water down your orange juice, but apparently you really, really do. Now this one says, what if you wanted to make it 80% juice? Do you suppose you'd just add half as much?
Yep.
As before? Well, let's check it out. All we have to do is change this to 0.8. And then our window, we probably want to change this to a 1 now, so we're sure we could see that 0.8. So you guys are saying 8 gallons. I don't know, it doesn't look like 8 gallons. Let's see. Second trace number 5. 0.57 gallons. Now, why not just half as much? Look at this big mess over here. Do you think that multiplying this by 1/2 would have that effect? It doesn't. There's all kinds of things going on in that equation. So just multiplying by 1/2 is not going to do it. So this, it's about those concentrations and thinning that down. All right, so we could put a no right here. So we checked that out. All right. How are we doing for time? Not yet? Okay. Well, I think maybe we better spend another day on this.
I think we're passing out. Your notes from me. Traveling.
Oh, 23 through 28 is just find the horizontal asymptote. That's about the degrees. 29 to 34 are the graph it all the way.
Tell 11:30. What do you expect me to do?
Does that mean the test gets moved back one day?
Work the night shift tonight.
Yeah. Is that
Hey.
it?
You are.
Like what?
Get you some graph paper.
See, Daryl, does that mean the test is getting moved back one
And
day?
that way we'll test on graph.
Alright.
What do you need?
So the test is Friday now?
We'll spend another day on that. I'll find the December sheet or something.
No, we'll be fine. Hey. Is it just like a good? Can you pass back your?
Oh, you just gave me ads.